Now, in this last section, we'll be looking at the total expectation theorem. And like I mentioned earlier, the total expectation theorem is really similar to the total probability theorem. In fact, it's based off of the total probability theorem. So we're going to start just by looking at the total probability theorem. And as you may recall, the total probability theorem gave us a way to look at a series of events, say A1, A2, and A3, and to calculate the total probability of this event B occurring by summing over each of the possible pre-events, if you will, the A1, A2, and A3, by summing the probability of this event, and this event occurring. As we sum all of those, we find the total probability of B. And to put that in equation form, like we've seen before, that would be that the probability of B is equal to the sum over all I of the probability of A sub I multiplied by the probability of B given A sub I. And as you may recall, each one of these was the probability of B given A sub I for each of those legs. So this right here would be the probability of A sub 1, and then this would be the probability of A sub 1 up here. So we would sum that across all possible paths, and that would give us the total probability of the event B occurring as long as we talk about every single partition. And you may recall that we viewed this probability of A sub I as a weight, a likelihood of each possible way to get to B. Now, with that in mind, let's go ahead and look at a slightly different version of this, specifically one that involves random variables. So in order for the total expectation theorem to work, the first thing that we can do is basically say, let's let our B, our event B that we had before, be equal to the random variable x being equal to a specific value of x. So we're replacing B, our thing that we're interested in, with this event that our random variable is equal to a specific value. With that in mind, we can then go through and replace all of our terms over here. So instead of saying that we have A1 intersected with B and A2 intersected with B, we now have A1 intersected with the event that the random variable x is equal to the specific value little x. Based on that, we can then say that the PMF of a specific value of x, the random variable x, is equal to the probability of A sub 1 multiplied by the PMF of x given A sub 1, and we can sum all of those up to A sub n. So we would say that in the nth case that the probability of A sub n multiplied by the PMF of x given A sub n for that specific value of little x. Hopefully that makes sense. Moving from there, we can really write the total expectation theorem. And so now that we've established an alternate way to write the PMF of a given value of x as a sum of multiple conditions, or the sum of all possible conditions, we can then say that the total expectation theorem, or the total expected value of x, is equal to the probability of A sub 1, so just the probability of traversing this first condition, multiplied by the expected value of x given A sub 1. And then we can sum that across all of the i's, all the way up to n, so that in the nth case, we would be taking the probability of A sub n and multiplying that by the expected value of x given A sub n. Again, really just a way to say, if we have a whole bunch of preconditions, our A sub 1 through A sub n, that the total expected value, the total E of x, would be equal to the probability of each specific condition occurring multiplied by the expected value of x given that condition. And we sum that across all possible conditions. Now, to hopefully make this a little bit more concrete, let's look at a quick example. let's say that we have a probability mass function for a random variable x that looks something like this. So we have 3 events here, and we can call these a sub 1, that any of those 3 values of x occur, 0, 1, or 2, would be a sub 1. And then we have another area up here that we would call a sub 2, and this is, again, the event that we get a 6, a 7, or an 8 out of our random variable x. So the probability then of the event a sub 1 occurring would be equal to the sum of each of these 3 possible events. So this would be 3 over 9, or 1/3. And then the probability of a sub 2 occurring would be equal to, again, the sum of all of these possible PMFs. So that's 3 times 2/9, or 6/9, which we can say is just 2/3. So we have the probability of a sub 1 and the probability of a sub 2. That's both of our events. Now, to utilize the total expectation theorem, we would then need to multiply each of these terms by their respective expected value of x conditioned on that event. So we can say that the expected value of x, our random variable, given that a sub 1 has occurred, is equal to the expected value within just this event, which is, well, 1. So in this case, the expected value is 1. We can also say that the expected value of our random variable x, given that the event a sub 2 has occurred, is equal to the expected value within this event a sub 2, which is 7. So now we have expected values for 2 separate events. And you'll notice that what we've done now is simplified these. As opposed to having this PMF that looks kind of like a stair-step function, we've created 2 uniformly distributed PMFs. So we've been able to break apart this PMF into multiple pieces. And in doing so, we, just by looking at the PMF, have been able to calculate these 4 values. This probability of a sub 1 being 1/3, the probability of a sub 2 being 2/3, the expected value of x given a sub 1, and the expected value of x given a sub 2. Again, just by looking at the graph. But the question is, can we calculate the expected value of x? And the answer is yes, and this is where the total expectation theorem really shows its power. The expected value of x for this specific PMF would be equal to, in general, the probability of a sub 1 multiplied by the expected value of x given a sub 1 plus all of those like we looked at on the previous slide. But here that's just equal to 1/3. That is the probability of a sub 1 multiplied by 1. That is the expected value of x given a sub 1 plus 2/3, that is the probability of the event a sub 2, multiplied by 7. That is the expected value of the random variable x given the event a sub 2. Well, this is relatively trivial to solve. This is 1/3 plus 14/3, which is 15/3, or we can say that the expected value of x is just 5. So what we've done is taken this PMF that isn't necessarily the prettiest thing to look at, right? It's that stair-step type function. And we've utilized the total expectation theorem to create different events, and based on those events, create easy PMFs to solve within those conditions for expected values, right? We said, where does this look pretty? Well, there's 2 buckets that look really pretty. So let me create 2 different events now, A1 and A2, so that I can calculate just the expected value of each event independently, and then sum those by their relative probabilities of occurring. And I very quickly was able to arrive at this 5 just by calculating 4 numbers, which again, we calculated effectively visually just by looking at the graph. So this is where the total expectation theorem really becomes helpful when it comes to solving probabilities of random variables.